Here in the mechanical design department, we've been informed that the cooling system will require a change in order to accommodate a more powerful processor including a CPU and GPU for a high-end field PG laptop. This change will need to include analysis and validation of the dimensions, tolerances, and assembly methods of the cooling plate, the highlighted part in this picture, as well as its clearance with the CPU and GPU. This design process is called GD&T Design Validation, and it is to ensure that downstream manufacturing can deliver optimal desired processor performance and minimize noise from the cooling fan while achieving total Six Sigma quality rate. GD&T stands for Geometric Dimensioning and Tolerancing. These feature control frames inside or GD&Ts of the cooling plate. Total Six Sigma or plus minus 3 Sigma quality rate is basically 99.73% good products at normal distribution or 2,700 bad products out of every million units. First of all, let's take a close look at the product. This is the field PG laptop, and here you can see the PCB board, the cooling system including the plate, heat pipes, heatsink, and the cooling fan, all assembled to the base housing of the laptop. The PCB is first assembled to the base housing and screwed down, then two blue thermal pads are pasted to the CPU and GPU, one on each. And then the cooling plate with the pipes are placed on top of the cooling pads and secured to the base housing with 4 spring-loaded screws. Now let's take a look at the design challenge at hand. Here is a cross-section view of the cooling plate, CPU and the cooling pad in between. The red line area is where the cooling pad gets compressed by the CPU. Adequate compression here is required for sufficient cooling effect, since the new high-performance CPU requires the thicker 1 mm cooling pad instead of the 0.5 mm pad for the base model. Gap between the cooling plate and the CPU now needs to be within the range of 0.42 mm to 0.62 mm. If the gap is too close, excessive pressure could damage the CPU. If the gap is too far, cooling effect is not optimal, and this could cause CPU to overheat and the fan to keep running, and you will hear the noise. Gap between the cooling plate and GPU has similar clearance requirement. All these gaps are controlled by the 4 spring-loaded screws that secure the cooling plate to the standoffs on the base housing. All 4 spring-loaded screws are tightened down manually or automatically with digital micro-torque screwdriver at preset torques that usually vary in ±6% range. Therefore, to set the torque at the proper value is the key to achieve desired gaps, hence to deliver optimal processor performance, minimum fan noise, and Six Sigma quality. Now you are looking at the field PG VSA model. The tree structure on the left side includes product breakdowns of assemblies, parts, features and tolerances, and assembly operations in the correct assembly sequences. In VSA simulation, components are first virtually fabricated according to their GD&T requirements, and then virtually assembled together following the shop floor assembly methods and sequence. VSA can simulate making thousands or more products to statistically predict assembly level fit and finish from part and process tolerances. During simulation you can visualize part and assembly varying due to tolerances and stack-ups. Here you can see the gap between the cooling plate and CPU vary for each build, some smaller and some bigger. Now you see the results of building 5,000 units of the field PG laptops. It shows 4.45% estimated out of spec for the gap between the cooling plate and CPU. This is about 95.55% good quality rate or 44,500 bad products out of every million units, as opposed to the required 99.73% Six Sigma quality rate or 2,700 bad products out of every million units. A close look at in the contributor report shows that the top 4 variation contributors combined account for over 65% of the total variation. These are all variability from the process of screwing down the PCB to the base housing. It seems we need to add additional screw constraints to further stabilize the PCB and reduce variability. The latest VSA Flex capability that leverages Siemens FEA technology can handle simulation of compliant parts like the PCB board here, sheet metal parts in automotive, and other flexible parts. As you can see here, VSA has internal meshing capability, as well as generating FEA input and output results for Flex simulation. You can see from the normal direction arrows, these are the original assembly constraints, and these are the additional constraints from the Flex assembly operation. Let's activate this Flex operation and run simulation again. Well, as you can see, the out-of-spec percent for the gap drops down to 1.82% from the previous 4.45%. We are now at 98.18% good quality rate, still below the required 99.73% Six Sigma quality rate though. Now it appears most of the out-of-spec products are with 2 big gaps, which could cause excessive CPU heat and fan noise. This problem probably can be solved by increasing the preset torque of the digital screwdriver to shift the gap downward a bit. Empirical data shows by increasing the torque from 1.72 Nm for the base model CPU to 2.25 Nm can press the spring-loaded screws down from the current 0.08 mm to 0.12 mm. We will change the displacement in the tolerance library, update the VSA model, and run the simulation again. Voila! Now we are down to 0.08% out of spec, or 99.92% good quality rate. Finally, we have a quiet yet high-performing field PG laptop at 6 Sigma quality with nearly no additional manufacturing cost. Well, at least on the paper. There are still a couple of steps need to be done to close out the quality loop. First of all the validated GD&Ts designed and validated here in VSA need to go into the master model, for example, here in NXPMI, ballooned and released. Optionally, 2D drawing can be generated from the master model. CMM inspection programs can then be generated directly by extracting the PMIs from the released model, simulated and optimized. Parts will then be manufactured and inspected. The shop floor inspection results will be automatically fetched in real time to populate the quality report templates in Teamcenter. These quality reports track top contributing critical to quality PMIs identified in the VSA studies earlier. Engineers can also investigate root causes of build quality issues in DPV interactive analysis environment. All these shop floor measured data can be accessed by VSA for data-driven simulation and updating the tolerance library, hence the quality loop is now closed. The entire process from using VSA for GD&T design and validation, NXCMM for inspection programming, and DPV for build quality reporting and analysis forms Siemens model-based quality solution. A true end-to-end quality engineering solution to help with achieving affordable quality.